Real quick, the state model, L of t for location. So you can use just xy if the thing is just translating. You can use a similarity transform, which is xy, rotation, theta, and a scale. That would be 4 parameters. Or you might do an affine deformation if you're going to allow things to skew a little bit. It doesn't really matter. You just have to have some model and some way of saying I'm going to be able to represent these elements. What's my dynamics model? Well, the dynamics model that they used was actually very simple. They said, and this is just written P of L1 given L0. You could write it as T plus 1 given T, but then I got to write all these T plus 1s. All right? And what you see here is a bunch of independent normal distributed variables, right? So what this says is that the x value is just normally distributed about the old x value with some variance, sigma squared x. Same thing with the y, same thing with the theta, same thing with the scale. So this is a similarity transform. What it says is nothing about how I move in x tells me anything about how I moved in y. That's the pure Brownian motion. So that can be illustrated like this, right? So here's LT. This is where I think the thing was at any time t. And what this Brownian motion says, well, at LT plus 1, maybe I'm right nearby, maybe I'm at the same place but oriented differently, maybe I'm over here, maybe I'm over there, maybe I'm over there, maybe I'm over here, where the likelihood of being in any of those locations depends upon how far I've moved. That's what these things here say, okay? So in other words, moving further away from my old y gets less and less likely. What you can do is you can imagine distributing a whole bunch of possibilities, and that's what's illustrated here as LT plus 1. And the idea is that the farther LT plus 1 is from LT, in terms of x, y, theta, and scale, or any of the other variables, the less likely it is. So that's our dynamics model.